So we're recording, and so question 5, we have trains carrying bauxite from Canada to New York State. They tell us that each train car is supposed to have a mean of 70 tons with a standard deviation of 0.9. And we're also told if the mean is greater than 70, the loading mechanism is overfilling. Essentially, we're almost running a hypothesis test without all the work that goes into it, but that's essentially what you're doing. You're saying, hey, the mean is 70, and we're going to test to see if it's greater. That's what we're looking for. So if the filling machine equipment is functioning properly, what's the probability that the weight of the ore in a randomly selected car will be 70.7 tons or more? So if it's functioning properly, the mean should be 70, and we want to know the likelihood that it's 70.7 or more. And a car, so we're talking about one. So let X be the weight of an ore car. And since they told me is normal, I go to my standard, write my equation, the Z equation, and then I plug in the mean is 70, the standard deviation of 0.9, and the X value of 70.7. Once again, now I could have done this as a normal CDF, as mentioned earlier, or I can go ahead and I'm going to go ahead and run it once again using stat test, Z-test, and in this case, mean is 70, standard deviation 0.9, X value of 70.7, and we have one car, so N is 1. So I end up getting a Z-score of 0.778 and a probability of 0.218. So there's about a 21% or 22% chance that a randomly selected car would look like that, okay? So that's, and that would get you full credit for part A. So suppose what the weight of an ore car of the ore in a randomly selected car is 70.7 tons. Would that fact make you suspect the loading mechanism is overfilling the car? Well, the initial response is, well, it's supposed to be 70 and it's 70.7. So yeah, I initially think that, but I look at the chance of it happening, and that happens about 22% of the time. And it's like, well, that's really not that uncommon. So it's because it's not uncommon, I would not suspect. So I would not suspect the mechanism is overfilling the car, so I've now answered their question. And then they say, justify my answer. And I'm going to say by random chance alone, 21.5% of the ore cars would weigh that much. So 21.5% is not that unusual. And if all I wrote was that 21.5% is not that unusual after I said that I would not suspect it, that'd be fine. But you need to say that you wouldn't suspect, that's your decision, and you need to say why, which is the 21.5%. Now I went on further, so while a 70.7 car is overweight, that would not be sufficient evidence for me to suspect that the machine was overfilling the car. And that's what I was getting at, is we are essentially heading really, really close to a hypothesis test with this type of problem. Because there's like, hey, what is 21.8%? Essentially, that's a p-value. It's the probability I'd get a test statistic this extreme, given that it was really making 70 points, that it was really 70 tons. So that's how it relates to hypothesis testing, which we'll be working on next week. If the filling equipment is functioning properly, what's the probability that a random sample of 10 cars would have a mean ore weight of 70.7? Now this is a really key thing. We have a sample of 10 and we're looking for a mean. So consequently, in this case, we're looking for the X bar. And that's the distinction between the X bar and the X, where here we had a randomly selected singular car, and here we have 10 cars with a mean weight. And since we're looking for a mean, that makes it an X bar. So let X bar equal the average weight of 10 ore cars. And since we're working again with a normal, I write my equation, but now it's changed to be for the distribution of means, which is x bar minus mu sigma divided by the square root of n. Now I want to go ahead and draw this picture, but it happens to be the same picture that I had earlier in part A with only one small adjustment. This is still a mean of 70. This is still 70.7, but this is no longer x bar, this is x bar. All right, and I'm looking for this area, but you can see that's the same as what we had here, except this was an x, where this one being an x bar. All right, so when I go ahead and plug in, I'm plugging in 70.7 for my x bar, 70 for my mean, and 0.9, and we have to adjust for sample size because we're talking about the distribution of means. Once again, I could do this as a normal CDF, but I believe it's substantially easier on this type of problem to use a z-test. So my mean is 70, my standard deviation is still 0.9, my x bar is 70.7, but I've changed my sample size from a single car to 10. And we're still looking for a greater than. And so now we end up with a much larger z-score of 2.46, and the probability of that is 0.00695, or 007 is what I rounded it to. All right. So the probability randomly selected group of 10 cars had an average weight of 70.7 tons or more is 0.07. So once again, this is like a p-value. This is the probability that the machine was operating correctly at 70. That's the likelihood. 0.007 is the likelihood that I would get that. Well, that's a pretty small likelihood, and that ties directly to part D. So based on your answer in part C, if a random sample of 10 cars had a mean or weight of 70.7 tons, would you expect that the loading mechanism is overfilling the cars? Justify your answer. And this is incorrect. I would suspect that the mechanism is overfilling the cars. Why? There's only a 0.007 chance, so it's not, I would not suspect. I would suspect that it's overfilling the cars. So assuming the machine was loading the cars properly, there's only a 0.007 chance where you get a sample mean of 70.7 tons or more. That's sufficient evidence. So basically I can say because 0.007 is so unlikely, there's sufficient evidence for me to suspect that it's overfilling. All right? So that's kind of the difference between using z equals x minus mu over sigma, a single value, and versus the formula using the sample means. So I'm going to